Okay, let's continue. Now, this one, the nutrient bottle you see in the ward, right, the hospital, it needs to be hang high up because we want the pressure to be high at the other end of the needle. Okay, so to allow the nutrient water to enter the patient's body. Okay, otherwise, if it's not high, right, it doesn't have enough pressure to enter the veins of the patient, right? Because you have the blood pressure, the veins also exert pressure. So you need to hang it high so that end of the needle, it has enough pressure to enter the patient's body. See, it's the same principle of the pressure of water. Okay, now let me ask you something. Let's say I take a container and this is okay, I drop a wooden block inside the water. Okay, this is surface, we call it a surface X, and at a certain height under the surface of water, which graph will shows the relationship between the pressure and the height? A, pressure, height, directly proportional. B, pressure, height, linearly proportional. C, pressure, height, exponentially proportional. D, this is like going down. Okay, so which one is the correct one? Imagine that if I gradually lower down my wooden block in the water. Okay, so as the height increase, of course, you know that the pressure increases, right? But in what way does the pressure increase? Is it exponential increase or linear increase or directly proportional increase? So you know that D is already out because as you increase the height, the pressure decreases. No, right? Now let's look at B. How do you differentiate between this one? B, at height 0, there is pressure. See, it's not starting from 0, meaning that this one is telling you that at the surface of the water, there is a pressure. In some case, it is true because it has the atmospheric pressure, but it's not the pressure from the water. All right. At the surface of water, there is atmospheric pressure, but not the pressure of water. So this one is out. B is also out. Now look at C. C, as you increase the height, the hatch, the pressure increases exponentially. No. Why? Because if you look at your formula, right, P equals to H rho G, P equals to H rho G, there's no square here. If there is a square, meaning that you have a quadratic graph, right? You learned about that in maths. Square, you have a quadratic graph, which is when you will get an exponential graph. All right? So simply looking at the formula, you know that C is also not a correct answer. So the correct answer would be A, right? As you increase the height, the height, the depth, the pressure will also increase. Okay, so the graph looks like this, straight line up. Okay, so that's about pressure of water. Now next, we look at pressure of gas. gas pressure and atmospheric pressure. Now, we talked about where does pressure comes from. It comes from the weight, okay? The weight of a solid acting on a surface, or the weight of the water acting on a body inside the water, right? Now, gas pressure is no different. Gas pressure comes from where? We look back all the way to the kinetic theory of matter, kinetic theory of particles, okay? Do you still remember the kinetic theory of particles? You have a container, okay? Now, container filled with air. Now, you know that the particles of air moves randomly, right? This is what we learned in Form 1. Particles of air moves randomly, bouncing one another in a random direction, right? Now, from here, what is causing the atmospheric pressure? So, look at the air. How does the air behave inside this container, right? It moves randomly. So when air molecules, they hit the wall, they bounce back. Okay, so I draw it enlargement here. One particle, it hits the wall, it bounces back. Right? Now, let's look at the physics. For each particle, there is a mass, right? The mass of the particle. So I write m. And then before the bounce, before it hits the wall, it is traveling at an initial velocity, right? mu. So what is this? Mu is momentum, right? You have mass and velocity, momentum. So the air particles contains momentum. So it hits the wall and it bounces back at a different velocity. That is the final velocity, right? But the mass is still the same. So mv. So what happened here? There is a change of momentum. So mv minus mu. There's a change of momentum. Now, from your impulsive force formula, Ft equals to mv minus mu. Still remember this one, right? Ft is what? Ft is impulse. Okay, impulse equals to the change of momentum. So if you take the t here, the rate of change of momentum, meaning that mv minus mu divided by t, how fast the air particle is bouncing off, how fast is the time of impact with the wall. That is the rate of change of momentum, or we call it the impulsive force, right? So every particles in the container is acting a force on the wall. That's the impulsive force. Imagine you have how many particles in this container? The air particles, many particles, right? So it is because of all these particles is acting the force on the container, okay, that gives rise to what we call it as the atmospheric pressure. All right, so I repeat, atmospheric pressure is all the forces that acted by the particles bouncing off each other. All right, so same atmospheric pressure at sea level on the earth is because of the air particles of the atmosphere that we are exposed to, right? It's acting on every object on the surface of the earth, on everything. All right, so you can also say that it is the weight of the atmosphere acting on our body. Okay, so from here, this force, you have P equals to F over A, right? So this is the impulsive force, and then you have the surface area. That's when you get the pressure. Now, I want you to write down this one, atmospheric pressure. There are a few different ways to write down atmospheric pressure. How much is the atmospheric pressure? It is 1 times 10 power of 5 PA. Okay, 1 times 10 power of 5 PA, or you can write nm squared. So this is the atmospheric pressure. Or sometimes you can also write in terms of another unit, we say that 1 atm. ATM, okay? Atmospheric stands for not the ATM machine. ATM stands for atmospheric. Okay, 1 atm. So you know that 1 atm is equal to 1 times 10 power 5. The third way to write atmospheric pressure is 760 millimeter Hg. What is this? This is mercury. 760 millimeter mercury. What does that mean? Meaning that if you take a container and you fill that up with mercury, okay, so this is mercury, the atmospheric pressure will push the mercury up in this test tube, and the height will be 760 millimeter. Okay, so the atmospheric is pressing the surface of the mercury until it reaches a certain height of 760 millimeter. So which is why we call it 760 millimeter mercury. This is also the atmospheric pressure. It's just the unit system is different, right? What else? We have another one. We can also say it is 1013 millibars, right? So, but we don't often use millibars in physics. Millibars is for the weather forecast. The people, they forecast the weather, they use this millibar. Okay, millibar. So 1 millibar is 100 Pascal. Okay, 1 millibar is 100 Pascal. So this one, to be exact, right? 这个其实是1.013乘10 power of 5，可是我们可以直接写1啦，没有问题的。Okay, it depends on the question, but usually we can just use 1 times 10 to the power of 5. Okay, so 4 different unit system of atmospheric pressure. Okay, so you write down this one, and then I'll go to the next slide. Okay, let's continue. When going up the altitude, does the atmospheric pressure decrease or increase? When going up, okay, let's say this is sea level. Going up, atmospheric pressure, atmospheric ATM pressure, what happened? Decreases. Why? Simply because the air is less dense. Okay, there is not as many air at high altitude as there are at the ground level. Okay, so less air particles, less pressure, less force, less pressure acted. So atmospheric pressure decreases. Now, what happens if you jump up to space, for example? You know, our body is, the atmospheric pressure is very important to our body functioning. Okay, because you see all the astronauts, right? They go out to space. They wear a very thick suit. The thick suit actually provides them the atmospheric pressure, like same as the one at the ground level. Okay, to keep their body functioning normal. Okay, what happens if without the suit? You go up to space, you jump up to the space for whatever reason without the suit. What will happen to your body? In vacuum, what happened? So you see, in vacuum, right, there's no air particles. Okay, let's say you're here. This is you. This is the Earth. You are living Earth. Okay, so around you, no air particles, and you're not wearing any suit. Meaning that no air particles means that the pressure is very low. It's like very, very low because there's no air particle around you. So what happens if you have a very low air pressure in your surrounding? If you try to hold your breath, okay, now if you try to hold your breath, right, in the vacuum, what happens is that the air particle in your lungs will burst your lungs. Why? Because you remember that air, it moves from high pressure to low pressure. Okay, every time you have a high pressure region and a low pressure region, the air particles will move from the high to the low. Okay, so if you try to hold your breath in vacuum because you want to breathe, right? You try to hold your breath in your lungs, so the air particles will tend to burst your lungs. So you cannot do that, right? So how? You cannot hold your breath. You cannot breathe. Okay, it is said that a human, right, a human body can only survive for the maximum 2 minutes in vacuum. All right. After 15 seconds, you pass out. You faint because lack of oxygen. All right. So same thing, without the atmospheric pressure around your body, your blood vessels, the water contained in your body, right? So our human body is made up of like 70% of water, right? So without the normal pressure, atmospheric pressure condition, this water will vaporize, right? It will easily vaporize. So your tongue, right? Your tongue got your saliva. So you feel that your saliva starts to become bubble, right? It really happened. This one actually happened. It's not bluffing. Really happened. They did one experiment during like 19 something. All the weird experiment comes from 19th century one, right? 19 something. The scientists actually did one experiment. So like they put a guy in a vacuum place. Okay, actually the experiment is not intended to like kill the guy lah. Okay, it's like an accident happened. The suit of the guy, the suit the guy is wearing breaks. Okay, it's like it broke. Then what happened is that this guy, he feels that his tongue, he starts to feel that like it's bubble because the saliva on his tongue is vaporizing, is turning into steam because of the surrounding pressure is different. All right, so easily it vaporizes. Okay, so the point is that we cannot survive in vacuum. Okay, and we need the standard atmospheric pressure to keep our body alive. Okay, same thing. Okay, now a few applications of atmospheric pressure. I'll just pick a few to talk about this one. For example, this one, you put a straw here, okay, and then you suck here, right? So water flows in from here. So as you suck the other end, you remove some of the air particles in the straw, this one, and also here, okay? So you are removing some of the air particles and you're creating a partial vacuum, right? Partial vacuum. So what happened is that the partial vacuum, again, what happened to partial vacuum is low pressure, right? Vacuum is low pressure. So you have created a low pressure region inside the straw. So what happened is the outside, the atmosphere is high pressure. So it will press the surface of the liquid, and then it will force the liquid to flow inside the straw and then to your mouth. Right? So this is also an example of how the pressure goes from high to low. All right? So same thing as airplanes, right? How does airplane fly? Okay, that one we'll leave it to the next lesson when we talk about the Bernoulli's principle. Okay, you have Pascal and Bernoulli's principle. In the next 2 weeks, I'm going to teach you that. Right? So same thing. This one. Okay, so another one is the one that we use to hold the very huge glass. They use the what they call the suction cup. Okay, looks like this. Like you stick on the huge glass, right? And then it automatically it sucks the glass towards it, right? This we call the rubber suction cups. So how does it function is that you put it on the surface, and then you have to press a button to remove the air inside here, so it becomes partial vacuum. Also same, partial vacuum. So what happened to partial vacuum? You have very low pressure. So what happens if you have a very low pressure inside? So the outer surrounding is high pressure, it will press onto the low pressure region. Okay, and that is when it is totally fit in, then you can carry the glass with you, right? Okay, so same thing. Vacuum cleaner, also same. Vacuum cleaner, if you look at the inside structure of the vacuum cleaner, this is the hose. Okay, sorry about my drawing. Okay, this is the vacuum cleaner, stuck here. What happens is inside the body of the vacuum cleaner, there is a fan. Okay, so this fan, a rotating fan. Okay, now this rotating fan, it will remove the air from the body of the vacuum, remove it to outside. Okay, so it's like spinning, then it will remove it. Something like it functions like your ceiling fan lah. Okay, like a reverse. Okay, it removes the air, it sucks out the air. Okay, reverse of the fan. Okay, so what happens is inside here, again you create what? 看错东西了，一下啊。Okay. So what happens is here also you create partial vacuum, and then outside atmospheric pressure forces the dust, all the particles, all the waste, the garbages, all inside the vacuum cleaner. Okay, so you can have you can read through this one actually in your book. There's many examples in your book. Okay, I'm just giving a few of the examples. Okay. We look at a few example calculation, and then there's a small part, the last part, then you can carry on with the exercises, right? So not done yet. You need more like 20 minutes. Okay, we look at some examples, exercises. Okay, let me get my exercise. Just a second. 4 examples here. Okay, this one you no need to write down. Later I will send you the note for this one. Just a reference for the. Okay, look at number 1. Diagram shows rectangular box of dimensions 10, 20, 50. Okay, so the weight of the rectangular block is 10 Newton. What is the minimum pressure? What is the minimum pressure? So you know that the pressure depends on how you put the block. Okay, it can lie flat or it can be standing up. Both you will get different pressures, right? So minimum pressure is when you have the maximum area. Okay, so in other words, you have it lying flat on the ground is where minimum pressure happens, right? Okay, so P equals to F divided by A. Force is the weight, 10N, divided by 0.1 times 0.2 times 0.50. 1000 PA. Okay, straightforward. So if I ask you what is the maximum pressure? Okay, so maximum pressure, then you know that it has to be standing up. Okay, so if standing up, your block becomes like this. Okay, now standing up, then the surface area is different. It is this one at the edge here. This is like 10 cm times 50 cm, right? Okay, this one I calculated the volume. Okay, some adjustment here. Area is 20, 0.20 times 0.20 times 50, right? 0.50. 0.20 times 0.50, then 100. This is 100 PA. So this one, the area is 0.1 times 0.5. Okay, so the surface area is different. It should be greater than 100 PA. Right, so the point is to you have to know that how to calculate the minimum and the maximum pressure by arranging the block. Okay, number 2. The tires of a car are inflated so that an area of 50 cm square of each tire is in contact with the ground. If the mass of the car is 1,600 kg and is evenly distributed between the 4 tires, what is the pressure exerted by each tire? Okay, meaning that let's draw the base of the vehicle. Okay, this is the base of the car. This is your tire. This, right? So you have the weight of the car is 16,000 Newton. We change it to Newton. Okay, 16,000 Newton. So it is evenly distributed between 4 tires. So you divide it by 4, you'll get like 4,000 Newton acting on each tire. Right? So 4,000, 4,000, 4,000, 4,000. Now the area of each tire is 50 cm square. Then you change to meter square. Right? 50 cm square change to meter square. Divide by 1,000, right? No, divide by 10,000. You will get 0.05 meter square. This is the area in meter. Okay, so pressure equals to force divided by area. 4,000 divided by 0.05. 80,000 Pascal. Okay, next one. Okay, number 3, a small room with floor dimensions 2 meter and 3.2 meter. The height of the wall is 2.8. If the air pressure is 1, now this is atmospheric pressure, right? Pascal. And the density of air is 1.21 kg per cubic meter. What is the mass of the air? Using the densities equation, right? Density equals to mass per volume. So mass equals to density times volume. 1.21 times volume, then you have to find the volume of the room. Okay, so 2 times 3.2 times 2.8. Okay, this is the volume of the room. So you get the mass is 21.68 kg, the mass of the air particles. Now, B, what is the atmospheric force? Atmospheric force acted on the floor of the small room. So you want to calculate what is pressure or what is the force acting on the base of the room. Okay, so from the pressure equation, we are still using the same equation. So P equals to F over A. Now atmospheric pressure is acting everywhere, right? Remember I said acting on every surfaces, acting on the wall, acting on the base is still the same. So 1.21 1 times 10 to the power 5 Pascal equals to force divided by area. Okay, so area, you take the area of the base, 2.0 times 3.2. Okay, so force equals to 64.0000 Newton. All right. Okay, the last one. Okay, so if liquid A and B, so you have two solutions here, both weighing 3 gram and 12 gram respectively, is mixed into a beaker. What is the mixture density when liquid A density is this one and liquid B density is this one? Okay, let me draw it out. Here you have liquid A plus liquid B. So this is the mixture A plus B. Okay, so A density is 1.5, B density is 1.2. Also, the mass for A is 3 gram. The mass for B is 12 gram. Now, assume volume of A and B no change, meaning that after you mix them, right, the volume is the total. Okay, no decrease and no increase. Okay, now from here you find the volume. So density you got, mass you got, then you can get volume, right? Volume VA equals to MA divided by density A. So that is equals to 3 divided by 1.2, 1.5, get 2 cm cube. Also you find VB equals to 12 divided by 1.2, 10 cm cube. So the total volume would be 12 cm cube. After you mix them, so what happened next? You want to find the density of the mixture, right? So you have the total volume, and then also you have the total mass. You just add up. 12 plus 3 is 15 gram. So here, find the density, mass per volume. 15 divided by 12. 1.25 gram centimeter cube. This is your answer. Okay, so we are going to stop here. We have like half an hour more, so